Hey, good evening, everyone. So we'll cover surface integrals today. And there's two types: surface integral of a scalar field, and then surface integral of a vector field. In terms of application, I mean, what does this really find? The surface integral of a scalar field. Think of some very thin surface. For an example, I can use aluminum foil. This would find if this right here, this function of x, y, and z represented the density, then evaluating that surface integral would actually compute the mass, the actual mass of that very thin surface. So we've done mass in this course before. We found the mass for what, a lamina? Then we found the mass for a solid. So now you're thinking, wow, I can actually find the mass of a very, very thin surface. And then we'll do surface integrals of vector fields. And when we do that, they call that the flux of the vector field across the surface. And so, for an example, in terms of application, what is this finding? Think of the vector field as being the velocities. They represent the velocities of some fluid at every point x. The velocity of fluid at every point x. Then this flux that we're computing, this would compute the quantity of fluid that flew through this surface, all right, per unit time. That's what it gives you. It gives you the quantity in terms of the double. So I'll start out with something like this. I'll write something. I'm going to take a problem in the textbook. But after I write it, we can think of what would this really mean if we want to put it in terms of like finding like the mass or something. So I'm taking this from the textbook, and they want you to evaluate this right here. Evaluate a double integral. They got the little s right there. They got just a y. That's all they have, the variable y, and then d capital S. So right there you can recognize just by the notation, is this definitely a surface integral. It's a surface integral, but is it a scalar field or a vector field? It's of a scalar field. And that's because you don't see this vector right here, that vector notation. Plus they didn't mention flux or anything. And I want you to evaluate this. They said, here's surface S. They said it's a helicoid. So it's R of U comma V. And they got it equal to U cosine V. U sine V. Hey, so there's the surface we're talking about. The spiraling ramp. So that's that spiraling ramp. Alright. What else did they give us? Well, they got to give us the limits of integration. How much of that surface? Because that thing keeps spiraling forever. And here's the limits they gave in this problem. They said, how about using U between 1 and 0, and V between 0 and 5. I'll just put a comma. Make sure I did that correctly. Yep, that's what they got. V goes from 0 to pi, U goes from 0 to 1. And that's what we'll evaluate. Do you all agree, just by that notation, wouldn't that just be a rectangular projection? Do you notice that? I mean, think of how they wrote this. We're just going to put those in the limits for our limits of integration. This will be just taking that surface projected over a rectangle. That actually makes things easy, doesn't it? It's like it's not a general region, so that's going to be the easy part. All right, I'm going to start by rewriting this in terms of the surface integral. It's the surface integral of a scalar field. And I'll put all this stuff down that you see here. But can we talk about what would this really find? How about this? Let's pretend that that y right here represents the density of the surface. Then when we compute all this, we will be finding the mass. Does that help? So just so you can relate it to something, we'll be finding. So if that y was like, hey, the density is, didn't they always use rho? All right, the rho of x, y, and z is a y. density is this, then we're actually finding the mass. This would be the mass. Okay, well let's work this out. I have to do F composed of. It's a lowercase f because it's a scalar field. I apologize. So I have to put this y here. F composed of the surface, then multiply by the magnitude of the cross product of the two tangential vectors r sub u, r sub v, r first partial with respect to u, the first partial with respect to v, and I'm just going to go from 0 to 1 and 0 to pi. I mean, I'll put dA right now, but that's how we're going to set it up. All right. Sometimes the hardest challenge is being able to parameterize the surface. Great news about this problem, they already did it for us. This is already parameterized. Do you see that? They're using U and V. So, we know this is going to go from 0 to 1, so let's start out. What goes here? I hope you find this simple, because that notation, everyone, looks very confusing sometimes. F composed of surface. Well, that's a y, so what do I put in substituting for that y? You got it right there. Does everyone got that? That's what's going there when you work this problem. You're like, oh, what does this all mean? This means that I'm going to substitute. There's x, there's y, and I will substitute that for that. And that's what's going to go here. Cool. So that's just going to turn into what? A double integral of that. So here's the challenge. I'm going to go off to the side to do that one. Let's go over here. What's the partial with respect to u? Let's do this cross product.
Negative sine v.
Negative.
Sine, right?
Negative.
Sine v.
And do I have to keep the u?
No.
Love it. So the derivative with respect to u of u cosine v, is it just this? I'm just step away. Is that right?
No, sine it should, right? Oh yeah, that's right. Yeah.
And I'm with you. We just got to be careful when, because it's partial derivatives. We keep doing integrals, then derivatives, integrals, then derivatives. But everyone's okay with that. That's the derivative with respect to u. Awesome. Because that would be like 5x. This is the constant. Keep the constant. Let's do that with respect to u.
Sine.
And what about that? 0. All right. So far so good on the first with respect to u. All right. Try with respect to v. Now, here comes the negative sign, right?
Yeah.
You got to keep the u in front. You all are good. Negative u sine v. What's the partial of this with respect to v? U cosine v. And this is simply just a what? Let's cross them. Let's cross them. Change that middle symbol. What's the x component? Whoops, sorry. What about the first column? That times that minus that times that.
The sine v.
You all agree. Sine v. Love it. Now I'm going to put that in negative. Cosine v times 1 minus 0 times that. Just negative cosine v. And I'll take those parentheses off. I just wanted you to think, oh yeah, we always change the sign when we do the middle component. Negative in terms of doing this cross product. If we're doing where I'm doing the determinant of a matrix. All right, now I'm looking at what we got here, everyone. Check it out, and I'm thinking, boy, I better leave myself a little more room, huh? Maybe that's good. I'm seeing it coming. So this times this minus this times this. So I get u times cosine squared v minus a negative. Well, then that's plus times
Sine squared v.
sine squared. Is that okay with that? Now, I highly encourage you to do something with this. Be simple. You can factor out the u, and you'll be left with a cosine squared v plus sine squared v. What is this equal to? That's just a 1. So this entire z component, don't leave it like that. Just make it u times 1, which is u. U. That's just u. I'll rewrite it. Cool. There's your normal vector to the surface. Right like that. Alright, let's go to work. Let's do this double integral. We're going to put, for this, letter y, so we're just going to put a u sine v there, right? U sine v. What goes here, though? We should find the magnitude. So later on today, we'll do surface integral vector field. You got to do a dot product with the normal vector, but in this case, he's exactly right. We need the magnitude of this. So what is the magnitude of RU cross RV? What's the magnitude of this? All right, I get the square root of sine squared v. What's the negative cosine v squared?
Plus.
Plus cosine squared v. Is that one a great? Because you square the negative, it becomes positive. And plus a what? Again, before you throw that up here, can you simplify that?
1 plus u squared.
Excellent. 1 plus u squared. So that's going right here. Ta-da. Then du dv. My limits, they give them to me. U goes from 0 to 1. The v goes from 0 to 5. This will give me the mass. Once we value it. That'll give me the mass, actually, if this was the density. That was the density of the surface. That's what we're finding, this very thin surface. A very thin spiraling ring here. So now we're left just doing a double integral. Well, you can do it in an iterated format, iterated manner. I break it up if I can. And I see 4 numbers. Can I write these as solo u's and solo v's? I certainly can, so that's what I'm going to do. I'm going to go from 0 to 5, all the v stuff. All right, sine of v, that's it. Multiply the integral from 0 to 1 of by u square root of 1 plus u. What's that? Negative cosine v 0 to pi. What's the negative? Negative 1. 1 minus. What's negative cos? 1 minus a negative cos of 0. So I'm getting 1 minus negative 1 on that, which is 2. And we'll just take this 2 and we will multiply it with this. How do you do that integral up?
U sub.
U sub, moving off to the side. Here's u equals 1 plus. Now, and this is weird. I'm going to do a u sub, but it already had a u, so let's make up another letter. You want to call it a k sub, a t sub, or something? I'll do a k sub. Let's do a k sub. Let k equal 1 plus u squared. So what's dk? 2u du, so what's 1/2 dk? U du, so I can do the integral? Yeah. I'm going to replace that and that with the 1/2 dk. 1/2 in front, square root dk, and just put my k back. That's good. So I'm using k because it already had the letter u in there. What's the integral of that? And we'll apply this to the answer. So I'll just go like this. Yeah, I'll go right around that vector. And we'll have this evaluated. This is, so let me carry that. 2 multiply, you get the half. Sure, you can make 2 times the half 1. What's that antiderivative? 2/3 of k to the
3/2.
3/2. I'll put my k back. 2 times 1/2 is just what? A 1? What's 1 times 2/3? 2/3. I'll put my k back. K was 1 plus u squared. We'll go from 2. So what's the final answer? What is the mass? 2/3 of, okay, what's a 1 plus a 1?
2.
2 to the 3/2 minus, now put a 0 in there,
So that's 1/3.
1 to the 3/2. What's 1 to the 3/2? There it is. Unless you want to write that as 2 square root of 2. Bob writes that as 2 square root of 2. Back up. 2 square root of 2. It's just found the mass. If that was, that's the. Super job with that, people. Right? It's kind of neat. None of this stuff. We're going to this remaining part of calculus 3, the surface integrals. It may look crazy or intimidating, but it's not that bad. Let's do another one of these. I'm going to do surface integral vector fields. So the one I would like to do, can we do one from the practice? How about number 7? It's another. It says find the mass of a thin funnel. The shape of a cone. I'll write all that. Can I erase this?